Good morning, everyone. Welcome, educators and students, colleagues, state leaders, family, friends, and NASA enthusiasts from throughout our great state of Nevada. My name is Craig Rosen, and I'm the Associate Research Scientist with the Desert Research Institute's Office of Education, overseeing community engagement and professional development. I also serve as Director of the Nevada STEM Networks under the Governor's Office of Science, Innovation, and Technology. I'm delighted to present this special event to you today. We would like to make this an interactive event, so please join me in conversation by asking questions or voting on questions to ask our guest by visiting www.slido.com using the event code NVMARS. You can see that screen right there. It's www.slido.com using the event code NVMARS. My first memory and interest in NASA happened 51 years ago when my parents took me to Disneyland on the day of the Apollo landing, and they broadcasted it live on a big screen right above the old ride Mission to Mars. I was hooked. I am a member of the Apollo generation. I was a witness to that one small step. Through the years, I was in awe at the building of the International Space Station. I celebrated and mourned the Space Shuttle program, and today I'm very excited to be a part of the education of this new generation, the Artemis generation, where in a few short years, we will be returning Americans to the moon and then to Mars. Among the brilliant minds leading NASA is our guest today, Dr. James Green. I was fortunate to meet Jim this past February in Washington, D.C. at NASA headquarters through an invitation from my friend Nisa Kaul. He was so gracious with his time, and he and I spent nearly a half hour chatting about the upcoming mission to Mars, which resulted in an invite for me to attend the launch. Due to COVID, the events surrounding the launch were scrapped and disappointment set in. But Jim made it up to me by offering to participate in this special Nevada conversation today. This mission is unique in that we will not only be landing a rover to search for life on the red planet, but we will also be launching a space helicopter for the very first time as well. There's no other person who can give us the inside scoop on this mission other than Dr. James Green. He's been NASA Chief Scientist beginning May of 2018. Dr. Green has been working for NASA for quite a number of years and has served in various positions through his career. He's written over 110 scientific articles, received numerous awards, and has been a leader over several missions, including the New Horizons spacecraft flyby of Pluto, the spacecraft to Mercury, the Juno spacecraft, the Grail spacecraft to the moon, the Dawn spacecraft to Vesta and Ceres, and the landing of Curiosity rover on Mars, just to name a few. Jim Green is a science rock star, and I'm delighted to welcome him to Nevada. Thanks so much, Jim, for participating in this special DRI Office of Education conversation. Take it away.
Thank you so very much, Greg. It was just a delight when you asked me to, have others join us on this fantastic journey to Mars. And we're going to start out by how do we get there? And then we'll talk about how we land and what we're going to do when we get there. So just a couple weeks ago, this was the scene down at Kennedy. This is what we call the fairing. And inside the fairing, in a capsule, much like what an Apollo capsule looks like, is the folded up rover Perseverance and the helicopter Ingenuity. All right, so it's all folded up inside this fairing, and then this fairing is picked up, and behind us from this view would be the rocket. They're assembling the rocket. All right, and so they then put the fairing on the top of the rocket, and then they roll it out to the launch pad. And so you can see the launch pad in this image. You see the three towers that are similar. Those are lightning rods, okay? And then you see actually the launch tower itself. And so the inset on the right indeed is that Atlas rocket, okay? Now, I was head of planetary from 2006 to 2018 before I became the chief scientist. So the planetary missions, we use these Atlas rockets all the time. It's got plenty of power to get us to where we want to go. So this is a spectacular rocket, a tremendous successful series of missions that it's really launched for. It's been the real workhorse. Megan, next slide, please. And so how does it work? What does it do? Well, it has a combination of launch engines, all right? So it's a liquid rocket in the core, but it also has solid rocket fuel that just burns, okay, in these white rockets that sit alongside the long rocket tube that we can see in the upper left-hand corner. And so as the rocket makes its way plowing through the atmosphere, and we expend these solid rocket motors, we drop them off. So they all fall off. Now the upper middle panel is now showing us in orbit, okay? This is indeed the last stage for which the capsule is on top of that. The fairing has fallen away, everything is ready to go. And so as we orbit just a little bit of the Earth and we get around the other side, Mars is in view, so to speak. We fire that last stage and off it goes. And then it jettisons the spacecraft. And that's in the upper right-hand corner. So you see the capsule, and then you see this ring that goes around this capsule. And that ring that goes around the capsule is actually a spacecraft. That's the spacecraft that's going to take the capsule to Mars, all right? And then on February 18th, as Mars comes into view, looming larger and larger and larger and larger, that image in the lower left is what will happen. That spacecraft will point the capsule, jettison it, and then that spacecraft will turn and fly by Mars. And now the capsule is on its way down. Now this means that we literally launched and then went to Mars's orbit and inserted the capsule into the atmosphere all in one stroke. Imagine it's just like American football, where the quarterback goes back for a Hail Mary, throws that pass, and as that football goes down the field, that runner is right there to pick it up. And in this case, Mars is right there to get this capsule inserted into the atmosphere. And so it is moving 13,000 miles per hour when it hits the top of the atmosphere of Mars. And we see in the middle lower panel what's happening, and that is where the spacecraft hits that atmosphere and has this ablation surface, and then that starts slowing it down because the friction of the plowing through the atmosphere, heating this heat shield is going on. And in fact, it can get to 2,500 degrees Fahrenheit. I mean, it's just an enormous temperature when you think about it. This capsule is larger than our Apollo capsule, all right? So if you've ever been to a museum and you've seen a mock-up or even seen some of our Apollo capsules, and they're huge, you know, they had 3 people in them and all the equipment. This thing is larger. Okay, and so then as it starts to slow down and gets down to about 300 miles per hour, we then pop a chute. And so the lower right-hand panel shows the chute deployment. Right after this, we drop that heat shield. And now the chute has less mass to haul. And what's exposed is the folded up rover sitting inside that capsule. Next slide, please, Megan. So what happens next after that heat shield falls away? It gets down to several hundred meters before we see that surface, and it drops Perseverance. It drops this rover, and that's that middle panel. You see just right after it drops, down it goes. Now, in addition to the rover and the helicopter, what's there is also a platform. And you see this in the lower right-hand panel. This is the retro rockets. This is what we call the sky crane. The sky crane then is holding on to the rover, and it slows down and gets to about 20 to 25 meters from the surface, okay, and then stops. Everything stops, and that sky crane hovers, and images are taken below the spacecraft, below where this rover is going to be set down. And if it's hazardous, that sky crane actually will move it and take more images and check the area. That's called terrain relative navigation. We've never done it before, all right? And then when we find that safe landing spot, it will start lowering the rover on these three lines. And when the rover begins to unfold, it now, is coming out of this origami kind of situation where we folded it all up. The wheels come out, lock, and then the rover is lowered. It touches the surface, and that means we've landed safely. The lines are immediately cut, and communication goes up to the sky crane, that platform that with retro rockets, it says, fly away. And the sky crane flies away and crashes somewhere else, 100 or 200 meters away from the rover. Next slide, please. So now we are on the surface. So where are we going? We're going to a very special place. It's called Jezero Crater. And to give you an idea how important this place is, let me take you back in time and describe what Mars used to look like 4 billion years ago. 4 billion years ago, Mars was a blue planet, okay? It looked like Earth. It would have clouds, it would have rain, and it'd have an ocean. In fact, the ocean in the northern hemisphere, 2/3 of that northern hemisphere was underwater, and in some places it was more than 1.5 miles deep. It's an enormous amount of water. And right on that ancient shoreline, rivers were feeding into the ocean. And so when you look at this image, you actually can see one of the ancient rivers. It's in the upper left part of the image. You see that windy mess, and there's the river. And then you see this area where it looks like a delta. If you took the water out of the Mediterranean or got rid of the Gulf of Mexico, what would you see at the bottom of the Mississippi and the bottom of the Nile? You would see these deltas. This is deposits coming from all over Mars that come into this river, flow down, and then sink as this river pours into that ancient ocean. Now, this, though, is a crater because over time, Mars would get hit with impacts. And in this case, here is a huge impact crater right on that ancient shoreline, right where that river was dumping into the ocean. And so you can also see the rim of the crater very nicely at the bottom of the image, but as you go around, that rim isn't really well seen, So in the upper right part of this panel, you see the rim is actually collapsed. And that's because water would fill into this crater, eventually pour over it, and go into the ancient ocean. So the ancient ocean is in the upper right-hand portion of this image, okay? So this is a spectacular place. And where we're going in this crater is in that black circle. Now that black circle is called the landing ellipse. It's actually just a little distorted. It's not quite a perfect circle. It's an ellipse. And it's no more than 10 kilometers in size. And you can see there's highs and lows. So there could be some areas that would be pretty dangerous to try to land this rover. We don't want it on a surface where it rolls down or rolls over. So the terrain relative navigation is going to be really important for us. Okay. Now this is where we're going to land. And we're going to do it all at once. And it starts at that launch pad. It goes all the way to Mars and goes right down and lands in that ellipse. That's like hitting a golf ball in New York and having a hole-in-one in LA. Okay? And so we're going to do this all in one stroke. So what are we going to do when we get there? Next slide, please, Megan. Well, this is the rover. And as you can see, we've colored Jezero crater, pardon me, right in that ellipse area where there's different types of mineralogy. In other words, sediments that have come down that actually reflect light differently than other sediments that tell us the mineralogy of the rock and the soils are different, we color those. And so what happens then is once we're in this area, we're then going to use this rover to go over this entire region, finding the right samples that we want. And we're going to use all these experiments to do that. Now, the first set of important experiments are right here on this arm. Now, on the end of this arm is a rock core, okay, a drill. Now, this drill is really an unusual looking drill. It is a tubular cylinder with blades at the very bottom that spins, and as it bores into the rock, it creates a sample. So you see my hand, and in my hand is a sample, and this actually was created by the engineering unit of that rock core at JPL, and it's a piece of granite. And so we bore that out, and indeed, then that gets encapsulated in this metal rod. And once it's encapsulated, it then is laid down on the surface, okay? Now, why do we want this rock record? Well, the rock record, just like here on Earth, are the pages of the history of the geology and evolution of our planet for our rock record. But for Mars, that will be in this rock record. Now, Mars today doesn't look like what I sounded. The ocean is gone. It is arid world. The surface is oxidized. That's why you see it, red nearly everywhere. And so consequently, this rock record is so important to us to help us determine how fast the climate changed on Mars. We talk about climate change here on Earth all the time. The climate on Earth has done nothing but change. And that's true on Mars too. We want to investigate processes that change climate. We want to understand how atmospheres and geology and potential life has affected climates, not only here on Earth, but on Mars. What's happened on Mars can happen on Earth. What's happened on Venus can happen on Earth. We are so lucky to have these three planets, these terrestrial planets, that enable us to understand the evolution of the Earth, because they are at different stages of their evolution. Now, the Sherlock and Pixel instruments will help us determine the structure of the outside of the rock we want to drill. And we have the ability to drill more than 40 of these cylinders. Now, the way that looks, it's like a piece of chalkboard chalk, okay? And for students, you know, that you may talk to that didn't live in that area, don't understand what chalkboard chalk is like a large Crayola crayon, all right? So we have a substantial amount of material to really tease out. And so that record is all about not only the history of the planet, but also whether there was life on the planet. All right, now why do I say that? On Earth, there are 4,700 minerals. 300 of them are made because of life. And so that rock record also contains indication of past life on this planet. So, in addition to Sherlock and Pixel, which examine the area and tease out structures before we do the coring, we have a whole series of other instruments that help out. The first one is SuperCam. Now, this is a combination French-US instrument, and it's actually a laser. And so this laser actually hits a rock and starts vaporizing it. And then it takes its spectrum. And when we see the spectrum, then we say, oh, we know what that is. We've got samples of that. Let's go over here. And so we're able then already to do a number of remote sensings before we get into the area that we actually want to core that rock. Now, also, you see these Mast Cam. You know, the Mast Cam, those are cameras. You can see the lenses of those cameras on either side of SuperCam. And let me tell you how tall that is. If I stood next to this rover, I can just put my eye right at Mast Cam, okay? This rover actually is a little taller than I am, and I'm 6'4", okay? This is the size of an SUV, all right? So this is more than a 1-ton rover, and it's an enormous laboratory. It's one of the most sophisticated missions we've ever done. Now, right below Mast Cam is MEDA. This is a Spanish instrument, and it measures the weather, okay? We need to know what the weather is on Mars. We want to know the winds, the pressure, the temperature. We have that on almost everything that's landed on Mars. And now we have enough information about that that we can do a global circulation of the weather on Mars. And so we understand these weather patterns. That's so important for us, not only to understand its atmosphere so that we can land things, but also for humans to be able to be on the surface, live and work. We also have on the back a retro reflector. This comes from Italy. This is a little instrument that doesn't require power. It just sits on the rover. And we would shine a laser on it and get that laser beam to bounce back so we know exactly where the rover's at. Now, in addition to that, the rover's powered by radioisotope power. And that means plutonium that sits and blows apart constantly. Okay, it's radioactive, blows apart. And we can rack that up and then take that decay of plutonium into other products and create heat. And then with a thermocouple, which gives us a voltage difference, we can charge a battery. So we run just like an iPhone does that's constantly plugged in. You plug your iPhone in, you're getting charge all the time. That's how this rover works. All these experiments are run by that multi-mission radioisotope thermal generator, MMRTG. Now, below that is a Norway instrument, and this instrument is a ground-penetrating radar. If we're interested in the rock record, we want to see the stratigraphy below us. This tells us how this might have formed, and it adds to our information about that rock record. Very important instrument, too. And then finally, we have an instrument called Moxie. Now, Moxie is a fabulous experiment that we as humans thinking about going to Mars are going to need the information from. This instrument takes in the CO2 atmosphere of Mars, zaps it, pops off an oxygen. So then that means carbon dioxide, C, and 2 oxygens. You pop 1 oxygen off, then you have a C and an O, and you vent that carbon monoxide, the CO, you're leaving the oxygen, okay? And so we do that in the morning, in the afternoon, in the evening, in each and every season. And we see what the efficiency is of gaining that oxygen and how much oxygen comes out of this process. So if you watch The Martian, everybody was worried about, did Mark Watney take his oxygenator? This is the oxygenator, okay? This is the one that provides oxygen. And by knowing how efficient that is on the surface of Mars, we're going to be able to then size it up for humans to be able not only bring the oxygen they need, but also create oxygen out of the atmosphere. Wonderful resource. Now, what's not shown here, which is an important instrument that I dearly love and apologize for not having it here, and nobody hardly talks about it, but I had it put on the rover. It is an audio microphone. We are going to listen to sounds on Mars, okay? Now, I don't expect that at night when the rover is sitting there, you know, munging data and doing a few things that we're going to hear crickets, okay? That'd be wonderful to think of, you know, but, you know, the winds and how the rover moves. And when the rover, you know, if there's metal on metal grinding, we'll hear that. And then that'll help us diagnose all kinds of engineering aspects of the rover. So it's we call it an engineering element, which is one of the reasons why we don't really show it. But to me, hearing the sounds of Mars will be fantastic. Next slide, please. So in addition to Perseverance, named by Alex Mather, a student, we had a student competition, and we've done that for the last several rovers. We love the name Perseverance, and he's given us the approval to call it Percy. You know, I like the nickname Percy. In addition to Percy, we have a helicopter, and the helicopter is actually going to sit underneath the belly pan of Percy, and we're going to drop it. All right, and so next slide, please. And then our rover is going to back up. Okay, next slide, please, and get to the point where we're far enough away, you know, probably 50 meters, maybe more, and we'll send the signal, turn on, okay? And this helicopter, also named by students, is Ingenuity. Now, Ingenuity is going to go through a series of flights. The first several flights, for instance, the first flight's going to be up, hover a little bit, and come down. Only go off the surface a few meters. The next flight will be go up, translate, maybe 10 meters, and then go down, okay? And then the next flight will be go up and go out, maybe 100 meters, and then come back and land in the exact same spot. You know, and so as we perform these maneuvers and get more and more used to flying a helicopter in an atmosphere of another planet, which we have never done before, once we've worked this out, if everything's working well, then we're going to put it into operation. And what we want Ingenuity to do is to image the area in front of Percy, to look for hazards, to be able to help us figure out the route that we want and get it to the surfaces that we're going to create this rock record by coring. Next slide, please. So let me end with what happens next. You know, what happens after Percy gets all its samples? Well, if you look at the Earth and then to the arc on the left, we're going to launch another mission that lands on Mars. So you can see the entry, descent, and landing, okay? And there it is, it's laying right there. And that is an ascent vehicle. It is a rocket. We're gonna land a rocket on Mars. This mission is targeted to go in 2026. And then we're going to have some fetch rovers. Now, what will come with it is probably a fetch rover that will run around and pick up from the ground our metal sleeves, the metal sleeves that contain those samples, and bring them over to the MAV, which is the Mars Ascent Vehicle. And then the MAV will be erected when all the samples are there that we're ready to bring back. We'll blast it off. And the last stage will push the capsule that contains these samples and put it in orbit. And then we have another spacecraft coming, getting into orbit and hunting it down, finding it and getting at it and docking and bringing it in, and then bringing it back home to Earth. And then dropping that capsule off, probably in the desert of Utah. We've used that many times, that area. And then we're going to acquire it and bring those samples into a BioLevel 4 facility, a facility that actually could manage anthrax if we wanted it to, and keep it contained. Now, why are we doing that? Because we need to know if the samples we're bringing back contain toxins. They probably will. And pathogens. They may or may not have pathogens. Those things that could hurt us as living beings here on Earth. Then we start that study, and once we interrogate the samples, we can then release them for further scientific analysis. And that will occur, and we'll have these samples back by the end of this decade. So that's the plan. And it starts with our launch, which launch window opens on the East Coast at 7:50 tomorrow morning. So with that, let me turn it over to Craig for answering any questions you may have.
Well, thank you, Jim. I can't believe all the information you shared and all the questions then that are coming in through our Slido app. So please, if you have a question for Jim, go to www.slido.com using the event code NVMARS. But I get the first question.
Have at it.
So you talked about the mission here, and what do you hope to find?
Okay. I think, okay, so what I hope to find is, this is a life detection mission. Not all of it. Many aspects of it are doing different things, as we talked about, supporting human exploration, measuring atmosphere, doing things that help support other missions in the future. The helicopter is indeed, if that works out, we're going to have helicopters all over the place on Mars coming up. You wait. But indeed, the rock record is really what I'm interested in. I want to know how the planet changed. Now I personally, I'm a magnetospheric physicist, okay? And what does that mean? That means, I never met a magnetic field I didn't like. Every time anything generates a magnetic field, I'm fascinated by it. The sun generates a magnetic field. The Earth generates a magnetic field. Our giant planets generate magnetic fields. And Mars did too, but it lost it. And losing that, and what happened to the climate after it lost it, is in that rock record. That's what I hope. But more than that, I hope we can find an answer to the question, are we alone? Did Mars support life in its past? It looks like it's got everything going for it. And that answer might be yes, that it did have life in the past. That will be in that rock record.
That'd be so exciting to really, here in the next decade, that there is truly life on Mars, and we'll get that proof when you bring back that core sample.
That will be proof. That's really key. Proof.
Yeah.
Scientists can talk about stuff all they want, but extraordinary claims, this is what Carl Sagan always said, require extraordinary proof. And there's nothing, absolutely nothing, like having that sample in your hand to say, it's right here.
I'm also fascinated that you included that microphone too, because I can't wait to hear the sounds of Mars.
Right.
I hit
I can imagine myself at work listening to the sounds of Mars and the, woo, what was that? Woo, let's get a picture of what Percy was doing at that time, and I think we're going to find some really fascinating things when we relate that data to what's really happening on Mars.
Yeah, I can't wait to hear it. So we've been getting a lot of questions, and my colleague Megan Collins is going to be asking some of them, the ones that have been voted most popular by the crowd here. So Megan, what's our first question today?
First question comes from Maria B. What advice would you give to undergraduate science students? What was the most challenging part of your academic journey?
Okay, there are several things that occurred to me that really is of fundamental importance, and that is in high school, I recognized I was good in math, I was good in science, and good in history, so I had a lot going for me. And my brother said one day, are you going to college? I said, yes. And he said, what are you going to major in? I said, I don't know. And he says, what are you good at? These are the things I'm good at. And he says, what are you going to do? And I cited, that science was it. It was also during a time when we had, I saw the Apollo landings. Okay. In high school, I ended up working in an observatory. I built instruments, cameras for the back of telescopes, and took astrophotography and even got some things published in Sky and Telescope while I was in high school, okay? And I watched the first episode of Star Trek from then on. I was inundated with the space environment. This is what's going to happen when we go to the moon again, all right? When we go what we call forward to the moon with humans, and we'll have the first woman and the next man, or perhaps the next woman after that, on the surface, walking around, taking samples, deploying instruments, and then not just for a few hours or a day, but many days, many weeks perhaps. And we want to keep that going so that they learn to live and work on a planetary surface, because we're going to go to Mars. So what does it take to get involved in that? Well, you got to have students that have this interest. And I can tell you that they need the fundamentals, okay? So getting them to say, okay, well, I want to know this advanced engineering. No, you need that fundamental. You saw how hard it was. It looked like a miracle that we're going to take this 1-ton rover, okay? This 1-ton rover, Perseverance, and put it on the surface of Mars. And each and every one of those steps involve mathematics and thermodynamics and orbit analysis and Kepler's theories. And so that's all built on the knowledge of each and every one of those fields. And so getting a fundamental knowledge is really important. But here's the most important part to me. It's not about how good you are in those areas. And in fact, in all the math courses, not all math is sort of created equal, in the sense that I did really well on some math. I could do a differential equation like that, but I wasn't crazy about geometry, all right? I didn't really do very good in geometry, all right? I just didn't have it. But that didn't stop me, all right? And it comes down to drive. It comes down to perseverance, the ability to work through those difficulties to meet that greater end. That is at least 70% of the challenge, is determination. So that's what I would recommend.
Your pep talk is making me want to go back to undergrad. Next question. So you mentioned that the moon mission is actually a bit of a practice run, or a learning run, so to speak. So the next question comes from MR. Mm-hmm. Can we make Mars habitable by making the Earth's surface processes quicker, releasing gases in the atmosphere to have a thick atmosphere? Maybe this relates to the Moxie instrument.
So indeed, many of us scientists not a huge group, but some of us are starting to talk about how to terraform Mars, okay? Such that it becomes a little more Earth-like in terms of our ability to live and work on that surface. Now, we're not going to be able to do it on the moon. The moon doesn't have a magnetic field, although it had one at one time, we have found out, okay? It's gone, and whatever atmosphere it had got dissipated long ago, and we're not going to get it back. But Mars is huge, and Mars has resources. And the water it lost was evaporated, and then it was broken up in the upper atmosphere, and then the solar wind, that's this outgassing that comes from the sun, which happens all the time. The sun is constantly outgassing. Sometimes it really gives you these huge bursts that we call flares and coronal mass ejections, and that causes all kinds of space weather. And here on Earth, we see aurora every time that happens. But on Mars, without a magnetic field, it just stripped the atmosphere, just stripped it away such that it broke the water cycle from liquid to evaporation to then transport to rain. So during that transport, it got stripped out. Well, then it didn't end up raining and getting back to the planet's surface. So it then began to dry out. And so the water then went, as we have, underground. All our underground water resources on Mars are actually vast. And in fact, the North Polar cap of Mars is full of water, but not completely. It actually has a veneer of CO2. You know, so CO2 snow happens every winter in the northern polar cap, covers the water that's there. If we melt that water, then 1/7 of the ancient ocean comes back. All right, and just like the dry valleys in Antarctica, you know, whenever there's rain, you get flowers. You know, and when there's no rain for years, no flowers. All right. We don't know if Mars would spring back to life if large amounts of water were able to stay on the surface. Right now, the pressure is too low for water to exist as a liquid for any time on the surface. You know, only seconds, all right, maybe minutes, but can't pool and can't create part of the water cycle that would then really hydrate the area. And so that's where terraforming comes in. If we can build up the atmosphere a little bit, then we can end up with certain levels of terraforming, and that will be important. So as we study those processes in reality are important for us to understand about this Earth. We talk, you know, humans are great terraformers. Look at what we're doing here on Earth. We're terraforming the heck out of the Earth, okay? And we're releasing CO2, and that is changing our temperature distribution. Can't help it. It's a greenhouse gas. How do we know that? The reason we know that are from scientists that are planetary scientists that worked on Venus, and they brought their codes to Earth. And we use those codes, Jim Hansen and his team, we use those codes to understand what will happen as we increase CO2 in our atmosphere. Well, we depend on fossil fuels, and CO2 gets released, but we need to think about how to manage that. And, you know, and maybe we should do what NASA does, and that is if we put CO2 in the atmosphere, we take it out. If we don't take CO2 out of the atmosphere on space station and do it every day, those astronauts would be dead. It's part of a cycle. It's part of a process. And so there are things like that we could do. And by studying terraforming and trying to understand these things and working on planetary scale issues, we will move ahead, and we will allow that to then help us survive into the future as a species.
Wonderful. Thank you. You mentioned that Perseverance is designed to look for signs of life. Can you elaborate on what signs you'll be looking for?
Yeah, that's a good question. So if you think about the rock record, you know, you think about fossils. You know, if life got to be complex and actually created structures and then bone structures and then died, then those structures could be in the rock record. And on Earth, we call them fossils. Complex life takes time to be able to evolve to. If all the conditions were right on Mars and life started out, you know, it may have actually started out like Earth, where we have much more of plant life taking, you know, that loves the CO2 and then generates oxygen, okay? That's the byproduct of the photosynthesis it receives. Now, when that stuff dies or falls in mud and then gets caked over, we actually can tease it out of the rock record. It then contains certain matrices, certain minerals, certain configurations, and you can see these ancient plants in the rock record here on Earth. So we then want to understand what we would find from Mars when we bring things back here by being geologists here on Earth and looking for the same basic conditions that were in the past, and then understanding, well, this is what we're looking for when we look in the rock record, because we see it in our rocks here on Earth.
Fascinating. So, the next question we'll take. How is Perseverance different from earlier rovers? What have you learned from past missions to improve this rover?
Yeah, really great question, because each and every rover we've done is a big improvement, okay? Now, Perseverance, you know, here it is a model of it. You know, this is as I said, it's about an SUV size rover, is like Curiosity, okay? In fact, I'm fooling you a little bit because this is actually a model of Curiosity, but it looks like Perseverance, okay? It's got a mast, it's got a box, and it's got instruments in it, it's got an arm, it's got an RTG here, it's got all the basic stuff, okay? But Perseverance has many more instruments and is a much more sophisticated rover and cores rock, okay? Once we realized we really needed to not just remotely analyze the geology, but bring it back, that's that next improvement. Now, each and every rover also has new advantages. You know, the first one we landed was Sojourner. Okay, that's like your microwave, you know, size of your microwave sitting on the counter, all right? So we landed that with airbags. Instead of dropping, you know, the sky crane, we dropped a capsule and inflated airbags, and then those airbags bounced, okay? And then we deflated the airbags and then extracted the rover out of it. We did that for Sojourner, and we did that for Spirit, and we did that for Opportunity, okay? But that won't work for Curiosity, okay, and Perseverance, because they're now too big, okay? Those rovers are a quarter ton. Curiosity is about a ton. Perseverance is more than a ton. It's almost a ton and a quarter, okay? And the additional mass, we now have learned how to land. So if we're going to continue to land more and more sophisticated instruments, we got to figure out how to land a much more bigger rovers, more mass to put down on the surface. Not only that, Curiosity's ellipse was about, landing ellipse was about 15 or so kilometers, okay, in a region that anywhere we land, it was flat. We already knew that. We didn't have terrain relative navigation, and now we have it for Perseverance. So that means we're going to land in a tighter ellipse and in an area that has hazards, and we're just going to maneuver around the hazards, find the right place, and bring it down. So each and every rover we make major improvements on, and that's how we learn to eventually put humans down on the surface of Mars. And in fact, as I mentioned, that microphone, we've never had it on any other mission. This is the first.
That is so cool. We're having
Thank you.
exciting weather here, so you lost me for a second when the power went out. So please bear with me.
Okay.
So you mentioned you mentioned in that last little comment about the topography. Why don't you tell us a little bit more about Jezero, the Jezero crater, the specific site where the Perseverance is going to land, and why it was chosen?
Okay. So it was chosen because, one, it's on the ancient shoreline of Mars. Okay. Why is that? Well, if we're looking for life, you know, where might it be? We have to think about how life may have started here on Earth. Many people, many of our scientists believe that perhaps it started in the ocean and then moved to the land. Okay, then that means the shoreline is an area where life from ocean learned to evolve to the point where it could then transition to land. And so that seems to be a good spot. It's a good idea to go to. And then on top of that, Jezero is so special because it also has this delta, you know, where all kinds of things out in Mars, hundreds of miles away, the sediments are flowing in. And maybe there's a dichotomy in terms of different types of plants or different types of fauna or flora that then, you know, have all kinds of emissions and leaves and things that fall in the river. And then that river brings it all the way down and dumps it into the delta, okay? So the delta at the bottom of that river, in the bottom of Jezero crater, is the huge attractor, all right? In addition to being on that ancient shoreline, it enables us to then look at these sediments and determine what's happened on Mars over a large region because it's come to us, all right? Now, we have a number of deltas in ancient rivers that have dried up that we've been to. And we've gone there and we've dug down and we've found spores. We found the material of past life when that stream or river was active, okay? So we have basic information about how important these deltas are, not only to bring the material in, but to protect it, to then put more material and sediments on top of it to preserve it. And so to me, you can't pick a better place. It's got all the right combination to make this a tremendous mission.
So cool. So this is going to be another question that draws on your experience. What can elementary teachers do?
Okay. So yeah, so I got grandkids, you know, and my grandkids love space, and you know, they know Grandpa works for NASA, and they ask me stuff, you know, so. Getting them the answers, feeding their curiosity, pointing out certain things that are happening, you know, talking to them about, you know, they're in Minnesota and they're in California. I'm in Washington, D.C. And of course, you know, I can't be there. But the next best thing I can do is FaceTime, and I can tell them, go out and see the comet, okay? and see what's happening in the universe around the Earth, okay, that we're privileged to be able to look out, see, and understand. And so by making them aware of the fact that we as an Earth circle the sun, and in that environment, we see different things. We see planets that also circle the sun. You know, we have a moon. What are the phases of the moon? Why is one side of the moon always points to it? Why are there dark spots on the moon? What does the far side look like? And where is NASA going to land? Okay, and then just get them the information, and let that then do what it normally does for children, is that enables them to ask more questions. And there are resources for our teachers. So hopefully my team is adding in the chat box some things that you can get access to and use.
Yes, they
Yes.
are. Please check the chat box, and you can look for all the resources that NASA's been sharing. Hey, Jim, I have another question, just because I get to ask them, okay?
Of course.
So, how long does it take, like, you're controlling this rover, you're controlling a helicopter. How long does it take to get information from Earth to Mars to do this stuff and then back again? So what's the time frame?
You bet, you bet. There is a time delay because we're traveling large distances. The orbit of Earth and the orbit of Mars means that as our planets go around the sun, they're in different locations in that orbit. Now, every 26 months, the Earth and Mars line up such that we can throw something from Earth and have it land on Mars. Okay, we're both on the same side of the sun, and we're both making that, you know, that arc in the orbit, and we just launch, and it just goes just as I said with the football analogy. Okay, that typically is about 7 minutes away. The shortest distance is 4 minutes light travel time. Okay, when Mars and Earth are just the closest they can ever be, it still takes 4 minutes for light to make it to Mars, all right? The longest is when, you know, that orbit is on the other side of the sun and we're on our side, is about 22 minutes. It's about 22 minutes. So that tells you right there that we can't joystick, you know, the rover. It's not gonna happen. So the rover's gotta have enormous intelligence associated with it to be able to receive commands, and those commands are, we want you by the end of the day to be there, okay? Go do it. And so here's a path. This is one of the reasons why the helicopter is so neat, could help us create that path. We have orbiters with high resolution imaging that are imaging all this whole huge area. That was one of the images I showed. Was from the Mars Reconnaissance Orbiter of Jezero Crater, you know, that, you know, right overhead. And so that rover then will be able to chart that path. And as it moves, if one of the wheels spins, it's going to halt because it may be in a sand trap. This is what happened with Spirit. Spirit moved into an area where it was a ancient crater filled up with Mars dust. You couldn't tell the difference. Went in too deep and we couldn't get it out, okay? And that dust on Mars is like talcum powder. So that was a real problem. So we have to automate this. So fields of computer science, not just engineering, not just celestial mechanics, you know, not just thermodynamics, but you know, computer software, artificial intelligence, you know, image processing, you know, those things that are so natural now to many kids as they're growing up are essential for our business, and they're all in this rover.
Wow. Megan, did you have, I think we have time for maybe a couple more questions. Do you have any on the queue?
Super.
Sure. Thank you, Jim. We really appreciate these, the time that you're taking today.
Not a problem, not a problem. So let me tell you, when we land on the moon, if you don't have me back, you're goofing up.
Oh, I'm signing you up right away. You're
okay.
good.
Okay.
Well, this question, I imagine that there are people who have looked back at Earth, the big blue marble, and just thought about the amount of international collaboration that these missions take. And you showed a slide with multiple flags. Could you share some of your experience collaborating internationally on this mission? Yeah, and it's not just this mission. Nearly every one of our missions, there's only been actually a very small number that have been completely NASA. But international cooperation to us is really important, and it's because there's a natural camaraderie that occurs between us scientists, and it transcends politics and boundaries. Okay, because science, the language of mathematics and physics
is universal. And we know we don't have all the ideas. We know we don't have all the creativity. And that creativity comes from diversity. It comes from different experiences. It comes from people that have different mental approaches even. And that's what we want to embrace. And so the diversity in our workforce, not only in our engineering, but in our science, is also reflected in our wanting our international partners to participate. And so the instruments on Percy, we had a call for instruments that was completely worldwide. Any organization in the world could propose an instrument on Percy, knowing what our objectives were. And so we received well over 50 proposals from countries all over the place. And it took us a while, but we were able to get the best proposals, connecting them all together such that we could get, you know, the kind of things that this rover is doing now together. And it turned out we had a wonderful set of international proposals that we accepted. So that's really important to us. That's really important to us. And that's going to continue. Think of space station, you know, look at all the countries, you know, I don't know how many dozen countries, several dozen countries were involved in building it. Several dozen countries, you know, are participating with astronauts, okay? You know, and in some of these countries, over time, sometimes we don't have good relationships. Sometimes there's a little tension there, but not on space station, all right? Not on space station. You leave that behind because every one of the crew depends on each other. To me, space station deserves a Nobel Peace Prize for what it has done to keep connecting us as humans together, and it represents the best in all of us.
That just gave me goosebumps, that statement. I just happened last night to track when it was going over.
Yeah, right.
Yeah, on the NASA website. So to people who haven't done that, it is really cool.
We also have an application. Yeah, we have an app for that. You know, we'll drop in the chat. Hopefully one of my people got it that can give you the URL, bring down an app, put in your zip code, tells you when space station comes over. Space station is the size of a football field.
Right.
You know, and it's up about, 250 kilometers or so. And so when it goes over, you can see it. It's pretty phenomenal. It's well worth doing. I'd even run upstairs at the top of the 9th floor at NASA headquarters in the middle of Washington, D.C. to watch it go over.
It was the brightest thing moving.
Yeah.
Yeah. So this will be the last question.
Okay.
You are the chief science officer.
Yes.
And leading missions that people generations ago could have only dreamed of.
Mm-hmm.
You have grandkids. There are a lot of children on this call. What are your dreams for science and society for your grandchildren's generation and beyond?
So to me, education is the heart of moving our society forward. Kids that get interested in space, get interested in technologies, may or may not end up working for NASA, but they're contributing. They're working with contractors, or they're at universities, or they're doing a variety of things. This is moving our country ahead, creating new products, creating new applications, creating the elements that we need to create a society that is technologically advanced. With that has to come a knowledge that goes beyond the Earth. Where are we in the solar system? it turns out we're not really in a very good orbit. The orbit of the Earth has some problems associated with it, all right? And, you know, the dinosaurs didn't have a space program. And so we have to watch out for where we are so that we then can continue to protect the Earth. For this species to survive, I feel firmly about this. We must be able to move humans from this planet into the solar system, living on the moon, living on Mars, truly creating, indeed, a mobile species for which the solar system is humanity's, all right? Let's explore it together. Let's be out there. That's going to be important. That's in their future. That vision that's so important for our society and for our species to be able to survive long term. If we don't do that, if we stay in our shell and we don't become educated about what these things I just mentioned, we will go by the way of the dinosaurs. And that will be a tragedy, not only for us as a species, but I believe us as a species in a galaxy of potentially other species that we could interact with. So let's get to the point where we can do that. That's in our future if we want it. And I want it.
And we'll work together for it.
Yep.
Good to you.
Thank you, Megan. Thank you, Jim. You know, in this day and age of distance learning that we're about to embark upon, NASA has been a leader in that for decades. So we have a lot to learn from all the work that you have done as we enter this new stage of digital learning and distance learning. You know, DRI is pleased to be partners with NASA, and we've been involved in research activities for many years. Our DRI scientists right here in Nevada work every day to conduct this important research, and I'm grateful to be able to celebrate their findings as they support NASA's missions. Our Office of Education has also partnered with NASA, and we have free resources to share with educators throughout the state, including our VR experiences, NASA STEM kits, and opportunities to check out a giant map of Mars. You can visit our webpage for more information. I want to thank each of you for attending today's event and pay special thanks to DRI's Office of the President, DRI's Office of Education Faculty, DRI's External Affairs Office, the DRI Foundation, Nevada Space Grant, my NASA colleagues led by Nisa Call, and of course, NASA's Chief Scientist, Dr. Jim Green. I encourage you all to wake up early tomorrow morning and watch this historic launch. I think it's scheduled, Jim said, for a 4:50 launch, but I think the live broadcast begins at 4 a.m. our time. So tune in and watch. I implore you all to stay healthy and stay safe, and look forward to our next opportunity together to share some amazing NASA stories and NASA research. Thank you all for attending today, and be well.
Thank you so much, Craig, for inviting me. It's been a delight.
Hey, Jim, I look forward to seeing you at the landing in February.
Yeah, February 18th, we're going to hit the surface.
I can't wait.
Softly.
Right. Thank you, everybody, for attending.